Welcome to Math with Professor V. I have a new integral of the day for you, and it's going to be a doozy, so grab a snack and get comfy while I work through this. If you want to try it on your own, feel free. My hint is the first step, you need to do partial fraction decomposition. So I'm looking at this. This is a rational function. The degree of the numerator is 3, and the degree of the denominator is 4, because we have x squared right here. So already I see, okay, degree of the denominator is higher than the degree of the numerator, which is a condition required in order to do partial fraction decomposition. And so I'm gonna go in that direction. Also, I'm looking at this denominator and it does not factor. X squared plus 2x plus 2, that's an irreducible quadratic. So do you remember how to set up partial fraction decomp in this case? It's gonna be a little spicy. So here we go. Let me write out left-hand side. I have the original expression. And then not only is the denominator an irreducible quadratic, it's squared. It's a repeated irreducible quadratic. So the first time I'm going to list it in the decomp, it's going to be to the first power. And then the second time I list it, it's going to be squared. We do this often with repeated linear factors. It doesn't come up so much to have a repeated irreducible quadratic, but the idea is still the same. And then again, since each of the denominators contains an irreducible quadratic, then the numerator has to be a linear expression. So ax plus b, and then this is going to be cx plus d. Do we got it? Okay, this just doesn't come up that often, so most people forget how to set it up. Now I'm going to multiply through by the LCD, so x squared plus 2x plus 2 squared, right? And then let's see, on the left-hand side, I'm just going to have the numerator, x cubed plus 2x squared plus 3x minus 2. And then when this distributes through, this entire denominator cancels. This will now just be to the first times ax plus b. And make sure you're keeping your parentheses. And then the nice thing is here, when I multiply it by cx plus d, the whole thing's just gone. So all I have here is cx plus d. Good? Okay, let's distribute. So we have x cubed plus 2x squared plus 3x minus 2 equals, this will be ax cubed plus 2ax squared plus 2ax plus bx squared plus 2bx plus 2b plus cx plus d. Let me double check I didn't do anything wrong. 2ax, bx squared, 2bx, 2bc. Yeah, good. Okay, now let's solve for the coefficients a, b, c, d. It actually turns out to be a pretty easy process, so don't be scared. What we're going to go do is identify the coefficients for corresponding powers of x and set them equal to each other. So what I mean by that is highest power of x that I see in this whole equation is x cubed. And the highest power of x, the coefficient of x cubed on the left is a 1. And on the right-hand side, the coefficients of x cubed, oh, there's just a. There's only 1. So boom, I already know a equals 1. Now let's work our way down. So x squared, coefficient of x squared on the left is 2. And then on the right, I have 2a plus b. So 2 equals 2a plus b. Okay, continuing the process, x to the first, we have 3x to the first on the left, and then 2a plus 2b plus c. So 3 equals 2a plus 2b plus c. And then x to the 0, or my constant term, that's going to be negative 2 equals 2b plus d. So negative 2 is 2b plus d. All right, very good. So now let's see. I already know a is 1. And then if a is 1, can you see that would be 2 equals 2. Okay, then b is 0. Great, I love it. B is 0. And then let's see, if I know A is 1 and B is 0, then over here I'm going to have 3 equals 2 plus 0 plus C. So C is 1, yes. And then lastly, I know B is 0. B is 0, yes. So negative 2 equals 0 plus D. So D is negative 2. Okay. I told you it wasn't going to be bad to solve, right? It just looks somewhat intimidating, but we're fine. We're hanging in there. So now I'm going to rewrite the integrand using the partial fraction decomposition, okay? Are you ready? So we have integral. It was 1x plus 0, because b is 0, over x squared plus 2x plus 2, plus c is 1, d is negative 2, and then this denominator was squared, right? X squared plus 2x plus 2 squared. And then parentheses, dx. So now I know I'm going to split things up and work on some integrals separately, but let me think about what's the best way to go about doing it, okay? Now, since this denominator does not factor any further, okay, and I do have x to the first in the numerator, you see how this is 1 degree higher than the numerator? I'm thinking u sub might be a nice choice for this first little integral here. So let's see, before I commit to anything, like if I were to let u equal x squared plus 2x plus 2, the whole denominator, right? Then du would be 2x plus 2 dx. And that's not what I have up top. I can factor a 2 out, that'll help. 2 times x plus 1 dx. And then I can say 1/2 du is x plus 1 dx. So really what I need here is not an x plus 0, but an x plus 1. Yeah? Can you see that? So what I'm going to do is make it happen. I'm going to make sure I have x plus 1 up there. So I'm going to rewrite this now as the integral x plus 1 over x squared plus 2x plus 2 minus 1 over x squared plus 2x plus 2. That way I can go ahead and do the u sub that I wrote over here for this first integral, okay? And then we're going to do a similar thing for the next one. I'm going to again let u be x squared plus 2x plus 2. And then I would love an x plus 1 up top, not this x minus 2. So if I make it x plus 1 minus 1, and then I still have minus 2, that's going to get regrouped into the following. Plus x plus 1 over x squared plus 2x plus 2 squared minus, and then now this minus 1 and minus 2 gives me a 3 over x squared plus 2x plus 2 squared dx. Okay, so these are the 4 little integrals that I'm going to work on. I'll repeat again what I was thinking, okay? I looked at the denominator, it's 1 degree higher than the numerator, so my first inclination is let's try to do a u sub, and it looks like things are working well. I just need x plus 1 in the numerator. So if I want x plus 1 up here, I'm going to add 1 and subtract 1. So here's me adding 1, subtracting 1, and then I already split it up. I'll do the same thing over here, because instead of x minus 2, what I really want is x plus 1 in the numerator. So since I added 1, I'm going to subtract 1 again, and then that last integral is going to be minus 3. Okay, we're all right? That strategy comes from just experience. So this is not the first time I've done an integral like this. If you go through the playlist, I've done a few that are similar, and just the more you practice, then you kind of know how to manipulate them better, okay? So let's number these guys. 1, 2, 3, 4. Now, integral number 1, we basically have done up above because we wrote out the whole u sub. So we have x plus 1 over x squared plus 2x plus 2 dx. And then this is my whole u sub, okay? So I don't really need to rewrite it. 1/2 du is x plus 1 dx. So here's x plus 1 dx. That's going to be, that's it, 1/2 du. 1/2 du over u. Good. So then this is going to be 1/2 integral du over u. And then antiderivative of 1 over u is ln, absolute value of u. I'm going to put plus c1. I'm going to save plain old c for the very end. And then now I'm going to go back, replace u with x squared plus 2x plus 2. And since that's an irreducible quadratic, I know it won't be negative. So I don't have to keep absolute value. I can switch to parentheses, plus c1. So there's my first integral done. Good? Okay, save it. You put it on the little back burner. It's simmering. You know when you watch the cooking shows and the chefs have like all these different pans going at the same time? That's us. This one, put it on the back. It's simmer time. Now let's work on integral number 2. You ready? Integral number 2. Here we go. So I'm going to keep the negative just so I don't forget what's going on. 1 over x squared plus 2x plus 2 dx. Now u sub will not work for this one because there's no x to the first up here. But since the denominator is squared, I'm going to try to complete the square. And probably this is going to be some kind of tan inverse. So if you'll recall, and this is an important integral to memorize, 1 over x squared plus a squared dx is 1 over a tan inverse x over a plus c. You can prove it using trig sub, but it's not worth doing that way, okay? It comes up so frequently, you should put this one to memory, okay? So similarly here, let's work through this next integral. And I'm going to have negative 1 over x squared plus 2x plus 2. That's going to factor into x plus 1 squared plus 1. And then I can see right here, I'm ready to go. This is a squared. And then this is my variable quantity squared. So all of x plus 1 is going to be what I have as my argument for tan inverse. So antiderivative here is going to be negative 1 over 1 tan inverse x plus 1 over 1 plus c2. That one's done. That was pretty relaxing, right? Look at us. Okay, third integral. Where is it? It's this guy. We're just going to use that same u sub that we did for the first one. Okay, let's go hop to it. So third integral is x plus 1 over x squared plus 2x plus 2 squared dx. If you forgot what the u sub is, I can write it here again. It's the same one, x squared plus 2x plus 2. du is 2x plus 2 dx. So 1/2 du is x plus 1 dx. So this time in the denominator, I'm going to have u squared. So we'll have 1/2, and then x plus 1 dx, that's my 1/2 du. Okay, so 1/2 is outside. I'm just going to put du in the numerator, and then we have u squared in the denominator. How are we up to here? Good. So then this is 1/2 integral u to the negative second du. Add 1, divide by the new exponent. This would be negative 1/2 u to the negative first plus c3. So this is going to be negative 1 over 2, and let me put u back in the denominator, plus c3. How was that? Not bad, not bad. Okay. The fourth one is the spiciest of all. Okay, so let's look at what was number 4. Here it is. Constant over the quadratic expression squared. It's similar to integral number 2. It's just you see how the denominator is squared now? So we can't use this antiderivative. No. What do we do instead? We trig sub, that's right. So we have negative 3 over x squared plus 2x plus 2 squared dx. So I'm going to complete the square again. Negative 3 over, this was x plus 1 squared plus 1 squared dx, right? So what's stopping me from this just being simply some form of tan inverse is the fact that this whole denominator is squared. So what we're going to do instead is a trig sub. And remember, usually if we have an expression of the form x squared plus a squared, we let x equal a tangent theta. Well, in this case, x plus 1 is my entire x squared, the variable quantity, and then a here is 1. So what we're going to do is let x plus 1 equal a, which is 1, tan theta. Okay, so you keep this whole guy together. That's all of it, okay? And then take the derivative, so dx would be secant squared theta d theta. Okay, let's rewrite the integral now in terms of theta. So I still have negative 3 over, instead of x plus 1 squared, that's going to be tan theta squared plus 1, and then this is all squared. And then my dx is secant squared theta d theta. Okay, very good. Now the whole point of doing trig sub is so that you can use a Pythagorean identity to simplify the integrand. And I know tangent squared theta plus 1 is secant squared theta, and that's all getting squared again. So right now, let's write things a little more neatly. I have negative 3 secant squared theta d theta over secant squared theta squared is secant to the 4th theta. What's next? I can cancel out this secant squared theta. Now this is just secant squared in the denominator. So we have negative 3 d theta over secant squared theta. We'll get that poor little secant squared out of the denominator. It's cosine squared in the numerator. And let's take the negative 3 out. Cosine squared theta d theta. What do we do here? Anytime you see cosine squared in an integral, you turn into a little math robot and you go, I will immediately replace it with 1/2 times 1 plus cosine 2 theta d theta, half angle identity. Okay, and then please take out this 1/2 with the negative 3. Always take the constants out. If I wasn't explaining right now what I'm doing, I would have done it immediately, okay? So negative 3/2, 1 plus cosine 2 theta d theta. We can take this antiderivative, no problem. This will be negative 3/2 times theta plus, now since there's a 2 in front of the theta, when I take the antiderivative, I'm going to have a 1/2 sine 2 theta plus c4. Boom. Okay. And then I know when I want to go back to x's, I'm going to need to draw a triangle and all that. And my triangle will be in terms of theta. So let's replace sine 2 theta using the appropriate double angle identity. So this is negative 3/2 theta plus 1/2 times 2 sine theta cosine theta. Are we good? Plus c4. And then these just cancel. Ba-dum, ba-dum. So now to get back in terms of x, like I said just a second ago, we're going to draw a triangle. And remember, we had originally let x plus 1 equal tan theta, right? Well, I want you to think of that as x plus 1 over 1, because tangent is the ratio of the opposite over adjacent side. So let me squish a little triangle in here. So tangent is opposite over adjacent. I can find the missing side using the Pythagorean theorem, and it's going to be that original expression we saw in the integral, rad x squared plus 2x plus 2. We didn't have the rad in the integral, but we had this x squared plus 2x plus 2. Okay, so now you should be able to go back to x land. We're in theta land right now. Negative 3/2 times this theta. You're going to come back over here where you made the trig sub. So theta is tan inverse of x plus 1. Use the trig function, the trig inverse function that was chosen for the substitution. That's typically the rule. Plus, now I need to know, what is sine of theta going to be? Sine is ratio of opposite side over hypotenuse. So that will be x plus 1 over rad x squared plus 2x plus 2 times cosine theta will be adjacent over hypotenuse. So that's 1 over rad x squared plus 2x plus 2 plus c4. And then, let's clean up. I'll distribute the negative 3/2 as well. So negative 3/2 tan inverse x plus 1 minus 3 times x plus 1 over 2. Okay, so this 3 I distributed to the numerator. The 2 will get distributed to this denominator, and these radicals will cancel out. So I just have 2x squared plus 2x plus 2 down there now. Do you see that? Plus c4. Okay. So we did all 4 little integrals. Let's put them together and clean up. The worst is over, but it didn't even feel that bad, did it? Okay, so let's make a dramatic narrative. At long last, if we take 1 plus 2 plus 3 plus 4, we have 1/2 natural log x squared plus 2x plus 2. I don't like how that looks, hold on. Minus tan inverse x plus 1 minus 1 over 2 times x squared plus 2x plus 2 minus 3/2 tan inverse x plus 1. I'm running out of room. Minus, and then let me distribute this, 3x plus 3 over 2x squared plus 2x plus 2 plus c, and then you got to tell the people where c equals c1 plus c2 plus c3 plus c4. Is this answer completely simplified? No. So I have negative tan inverse of x plus 1, negative 3/2 tan inverse of x plus 1. I can combine those. Minus 1 minus 3/2 will give me minus 5/2. So let's get that started. This 1/2 natural log is the only natural log, so that's going to stay put. That's our front runner. Let's put them at the beginning of the integral. Now I have minus 5/2 tan inverse x plus 1. And then look, these guys already have a common denominator. Do you see that? 2 times x squared plus 2x plus 2. So let's combine their numerators. Now be careful. This is a negative 1. And then this negative applies to both the terms in the numerator. So this is really like negative 3x minus 3. Minus 3 and minus 1 is minus 4. But if I keep the negative outside, then I'm just going to write 3x plus 4. Yes? Okay, take a minute to think about it if you're struggling with negative signs. That's normal. And then plus c. And that's it. Oh my goodness, that's it. And I actually really liked it. I would never put this on a test though. That's just me. I can check that my students know how to do trig sub and u sub and partial fractions without frightening them. You know what I'm saying? There's a way to test these skills and not torture someone like this. But it's a fun challenge just to see if you can keep everything straight and if you're able to recognize, you know, your typical integration techniques, but in a maybe like unconventional way that we have to use them in this problem. So tell me how you liked it. If you hated it, I totally understand. And comment down below. Let me know what your favorite part was. Let me know where you're watching from. And give the video a thumbs up. Subscribe if you haven't already. If you need to review any of the integration techniques that I used in the video, then go to the description box because I have all the videos linked from my Calculus 2 video lectures. And if you need to review any Calc 1 topics or pre-calc or trig, I have videos on that. They're all organized into playlists on my YouTube channel. And please follow me on Instagram, TikTok, Twitter, Math with Professor V. I love you all. I'll be back sooner than later. Bye.